Welcome back to FuzeTox channel. In this video we will see another article and let's read Applying Solid Principles in React. As the software industry grows and makes mistakes, the best practices and good software design principles emerge and contextualize to avoid repeating the same mistakes in the future. The world of object-oriented programming, OOP in particular, is a gold mine of such best practices, and Solid is unquestionably one of the more influential ones. Solid is an acronym where each letter represents one out of 5 design principles, which are Single Responsibility Principle, SRP, Open Closed Principle, OCP, List of Substitution Principle, LSP, Interface Segregation Principle, ISP, and Dependency Inversion Principle, DIP. In this article, we'll talk about the importance of each principle and see how we can apply the learning from Solid in React applications. Before we begin, though, there is a big caveat. Solid principles were conceived and outlined with object-oriented programming language in mind. These principles and their explanation heavily rely on concepts of classes and interfaces, while JS doesn't really have either. What we often think of as classes in JS are merely class lookalikes simulated using its prototype system, and interfaces aren't part of the language at all, although the addition of TypeScript does help a bit. Even more, the way we write modern React code is far from being object-oriented. If anything, it feels more functional. The good news, though, software design principles such as Solid are language agnostic and have a high level of abstraction, meaning that if we squint hard enough and take some liberties with interpretation, we will be able to apply them to our more functional React code. So let's take some liberties. Single Responsibility Principle, SRP, the original definition states that every class should have only one responsibility, aka do exactly one thing. This principle is the easiest to interpret, as we can simply extrapolate the definition to every function, model, component should do exactly one thing. What of all 5 principles, SRP is the easiest to follow, but it's also the most impactful. One is drastically improves the quality of our code. To ensure our components do one thing, we can break large components that do too much into small components, extract code unrelated to the main component functionality into separate utility functions, encapsulate connected functionality into custom hooks. Now let's see how we can apply this principle. We'll start by considering the following code example component that displays a list of active users. Const active user list, arrow function, const user set users, use state hook, use effect hook, load users, async await, response, JSON, const week ago, new date, week ago, set date, return, blah blah blah. Although this component is relatively short now, it is already doing quite a few things. It fetches data, filters it, renders the component itself as well as individual list items. Let's see how we can break it down. First of all, whenever we have connected useState and useEffect hooks, it's a good opportunity to extract them into a custom hook. Const users, set users, useState, useEffect, load users, return users, const active user list, const week ago, return. Now our users use users hook. So where is use users? Yeah, we have a new hook, const users, in the top of the code snippet. Now our use users hook is concerned with one thing only, fetching users from an API. It also made our main component more readable, not only because it got shorter, but also because we replaced the structural hook set that you need to decipher the purpose of with a domain hook, the purpose of which is immediately obvious from its name. Next, let's look at the JS6 that our component renders. Whenever we have a loop mapping over an array of objects, we should pay attention to the complexity of this JSX it produces for individual array items. If it's a one-liner that doesn't have any event handlers attached to it, it's totally fine to keep it in line. But for a more complex markup, it could be a good idea to extract it into a separate component. Const user item, return const active user list, return. Just as with the previous change, we made our main components more and more readable by extracting the logic for rendering user items into a separate component. Active user list, user item, yeah. Finally, we have the logic for filtering out inactive users from the list of all users we get from an API. This logic is relatively isolated and it could be reused in other parts of the application, so we can easily extract it into a utility function. Const get only active users arrow function, return users filter, const active user list, return user item, ul get only active. At this point, our main component is short and straightforward enough that we can start breaking it down and call it a day. However, if we look a bit closer, we will notice that it's still doing more than it should. Currently, our component is fetching data and then applying filtering into it. But ideally, we would just want to get the data and render it without any additional manipulation. So as the last improvement, we can encapsulate this logic into a new custom hook. Active users, use active users, active users, not map. Here we created use active users, it's here. Hook to take care of fetching and filtering logic. We also memorize filter data for good measures. With use memo. While our main component is left to do the bare minimum, render the data it gets from the hook. Now, depending on our interpretation of one thing, we can argue that the component is still first getting the data and then rendering it, which is not one thing. We could split it even further, calling a hook in the component and then passing the result to another one as props, but I found very few cases where this is actually beneficial in real-world applications. So let's be forgiving with the definition and accept rendering data the component gets as one thing. To summarize, following the single responsibility principle, we effectively take a large monolithic piece of code and make it more modular. Modularity is great because it makes our code easier to reason about. Smaller models are easier to test and modify. We're less likely to introduce an unintentional code application, and as a result, our code becomes more maintainable. It should be said that we've seen here is a contrived example, and in your own components, you may find that the dependencies between different moving parts are much more intertwined. In many cases, this could be an indication of poor design choices. Using bad abstractions, creating universal do-it-all components, incorrectly scoping the data, etc., and thus can be untangled with a broader refactoring. So I don't agree with them when we split our code into small pieces. When we have a lot of small pieces, it's fucking your brain. It's very bad choice for the production. We can split our code into small pieces. It's arouse a lot of small single responsibility components. It's works in the ideal world, not the real world. OCP states that software entities should be open for extension but closed for modification. Since our React components and functions are software entities, we don't need to bend the definition at all, and instead we can take it in its original form. The open close principle advocates for structuring our components in a way that allows them to be extended without changing their original source code. To see it in action, let's consider the following scenario. We are working on an application that uses a shared header component on different pages. And depending on the page we are at, header should render a slightly different UI. Cons header, arrow function, cost, path name, use router, return, path name, dashboard, link, home page, dashboard page. Here we render links to different page components depending on the current page we are at. It's easy to realize that this implementation is bad if you think about what will happen when we start adding more pages. Every time a new page is created, we'll need to go back to our header component and adjust its implementation to make sure it knows which action link to render. Such an approach makes our header component fragile and tightly coupled to the context in which it's used, and it goes against the open-close principle. To fix this problem, we can use component composition. Our header component doesn't need to concern itself with what it will render inside, and instead it can delegate this responsibility to the components that will use it using children pro. Cons header, children, cons home page, cons dashboard page. With this approach, we completely remove the variable logic that we had inside of the header, and now we can use composition to put there literally anything we want without modifying the component itself. A good way of thinking about it is that we provide a placeholder in the component that we can plug into. And we are not limited to one placeholder per component either. If we need to have multiple extension points, or if the children prop is already used for a different purpose, we can use any number of props instead. If we need to pass some context from the header components that use it, we can use the render props pattern. As you can see, composition can be very powerful. Following the open-close principle, we can reduce coupling between the components and make them more extensible and usable. Open-close principle, it's a very good principle. It works in production applications, and it also works in pet projects. List substitution principle. Overly simplified, LSP can be defined as a type of relationship between objects where subtype objects should be substitutable for supertype objects. This principle heavily relies on class inheritance to define supertype and subtype relationships, but is not very applicable in React since we hardly ever deal with classes, let alone class inheritance. While moving away from class inheritance would inevitably bend this principle into something completely different, writing React code using inheritance will be deliberately creating bad code which React team highly discourages. So instead, we're just going to skip this principle. Nice, they just skip this principle, yeah. Interface segregation principle. According to ISP, clients should not depend upon interface that they don't use. For the sake of React applications, we will translate it into components shouldn't depend on props that they don't use. We are stretching the definition of the ISP here, but it's not a big stretch. Both props and the interface can be defined as contrast between the object component and the outside world, the context in which it is used. So we can draw parallels between the two. In the end, it's not about being strict and yielding with the definitions, but about applying generic principles in order to solve a problem. To better illustrate the problem ISP is targeting, we will use TypeScript for the next example. Let's consider the application that renders a list of videos. Type video, title, type props, cons video list, items, thumbnail. Our thumbnail component that it uses for each item might look something like this. Type props, video const thumbnail, video props. The thumbnail component is quite small and simple, but it has one problem. It expects a full video object to be passed in as props, while effectively using only one of its properties. To see why that is problematic, imagine that in addition to videos, we decide to display thumbnails for live streams as well, with both kinds of media resources mixed in the same list. We'll introduce a new type defining a live stream object. Type live stream, name, preview, URL. And this is our update for video list component. Type props, items, array, const video list, items, return thumbnail video equal to item. As you can see here, we have a problem. We can easily distinguish between video and live stream objects, but we cannot pass the latter to the thumbnail component because video and live stream are incompatible. First, they have different types, so TypeScript will immediately complain. Second, they contain the thumbnail URL under different properties. Video object calls it cover URL, live stream object calls it preview URL. That's the crux of the problem with having components depend on more props than they actually need. They become less reusable, so let's fix it. We'll refactor our thumbnail component to make sure it relies only on props it requires. Type props, cover URL string, const thumbnail, arrow function, cover URL. With this change, now we can use it for rendering thumbnails of both videos and live streams. Type props, items, array video, live stream, const video list, arrow function, thumbnail, cover URL, item cover URL, or item preview URL. The interface segregation principle advocates for minimizing dependencies between the components of the system, making them less coupled and thus more reusable. Dependency inversion principle, DIP. The dependency inversion principle states that one should depend upon abstractions, non-concretions. In other words, one component should directly depend on another component, but rather they both should depend on some common abstraction. Here, component refers to any part of our application, be that a React component, a utility function, a model, or a third-party library. This principle might be difficult to grasp in the abstract, so let's jump straight into an example. Below, we have login form component that sends user credentials to some API when the form is submitted. Import API from common API, const login form, arrow function, email, set email, use state, password, set password, use state, handle submit, async. In this piece of code, our login form component directly refers to the API model, so there is a tight coupling between them. This is bad because such dependency makes it more challenging to make changes in our code, as a change in one component will impact other components. The dependency inversion principle advocates for breaking such coupling, so let's see how we can achieve that. First, we are going to remove direct reference to the API model from inside the login form and instead allow for the required functionality to be injected via props. Type props, on submit, promise, const login form, use state, handle, submit async event, prevent default, on submit, return. With the change our login form, in this component no longer depends on the API model. The logic for submitting credentials to the API is abstracted away via onSubmit callback, and now it is the responsibility of the parent component to provide the concrete implementation of this logic. To do that, we'll create a connected version of the login form that will delegate from submission logic to the API model. Import API from common API, const connected login form, const handle submit async email password, await API login email password. So we just move the logic from the one module to another. It's we just create another file, another chain of callbacks. It's maybe more easier to understand, but it's not easy to code it. That's too hard to use it. Connected logic form component serves as a glue between the API and logic form, while they themselves remain fully independent of each other. We can iterate on them and test them in isolation without worrying about breaking dependent moving pieces, as there are none. And as long as both logic form and API adhere to the agreed common abstraction, the application as a whole will continue working as expected. In the past, this approach of creating down representational components and the injecting logic into them was also used by many third-party libraries. The most well-known example of its Redux, which would bind callback props in the components to dispatch functions using connect higher-order component HOC. With the introduction of hooks, this approach became somewhat less relevant, but injecting logic via hooks still has utility in React applications. To conclude, the dependency inversion principle aims to minimize coupling between different components of the application. As you have probably noticed, minimizing is somewhat of recurring them throughout all solid principles. From minimizing the scope of responsibilities for individual components to minimizing cross-component awareness and dependencies between them. Conclusion. Despite being born out of problems of the OP world, solid principles have their applications well beyond it. In this article, we have seen how, by having some flexibility with interpretations of these principles, we managed to apply them to our React code and make it more maintainable and robust. It's important to remember, though, that being dogmatic and religiously following these principles may be damaging and lead to over-engineered code, so we should learn to recognize when first decomposition or decoupling of components tends to introduce complexity for little to no benefit. So, this article providing us the opinion that we just don't use one principle in React because it's no use case in React. So how he write? Risk of substitution principle. React team highly discourages, so instead we're just going to skip this principle. He skipped this principle in React, but he wrote about how to use solid principles in React. That is not a good article. I think he can write in more better way. So I'm disappointed. This article, the previous article, was better. So thanks for watching. Bye.